Alrighty, area between curves, part 2. On this particular video, we're going to do a couple where there's an intersection between. That won't be all of what we do, but there are basically just a couple of things beyond the ordinary ones that we dealt with in the last one, okay? And let's call those the wrinkles, okay? The wrinkles are, one, sometimes there is an intersection, okay, in the midst of the interval, okay? And what I mean by that is you have, you want to go from A to B, and this curve is underneath the other one for the first part of the interval, but on top being the more positive one on the second part of the interval. And that requires us to find that point of intersection in the midst of the interval and actually hash it out from there, okay? The second wrinkle is that sometimes we're going to do it with respect to y. And that means if I am given, something like this where there's not functions, okay, and I want to go from C to D, I need to figure it out with respect to my y variable, okay? Would need to solve stuff in terms of x, blah, 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 x is equal to blah, 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 and x1 and y1 instead of y1 and y2. X1 and x2 instead of y1 and y2 would be how I would do that, okay? The third one is just going to be ones that are just calculator intensive, and you just have to know how to jockey with your calculator, and that's really not that big of a deal. We'll do a couple of examples on that. So the wrinkles, that basically things that deviate from the norm, in which basically I set that out in part 1 of these videos, is where there's an intersection in the midst of the interval, where we're doing it with respect to y, meaning the cross sections are horizontal, right? Instead of in terms of x. And the third one is when you need your calculator to actually execute that particular integral. Alrighty, well, let's do one that has an intersection in the midst of the interval. So how about we do f of x is equal to x minus 1 cubed, and g of x is equal to x minus 1. All right, that winds up being just a little bit more robust. So let's figure out exactly where these intersect, okay? And they intersect, so let's go ahead and set them equal to each other. Now, the Algebra 1 student that is deep down inside of us, that Algebra 1 student that never dies, is thinking to yourself, oh my gosh, I just need to go ahead and multiply that out. But I don't like binomial expansion. And then you start worrying about it, and then you forget that, you really don't have to. Okay? Because if I pull x minus 1 to the other side, then this is basically quantity cubed minus quantity. Can I just go ahead and pull one of those out? I sure can. Okay, and that of course becomes x minus 1, and then this becomes x squared minus 2x plus 1, right, when I FOIL that out. Well, that plus 1 and that minus 1 cancel, and therefore I'm left with x squared plus 2x, minus 2x, and therefore x minus 1 times x minus 2. And therefore we find out that these actually intersect at 0, 1, and 2. Okay? Well, that shouldn't be too hard for us to fathom. We should recognize what this is right here. This is, of course, it's the parent of the cubics just moved over 1, right? And therefore it should look something like that, and then x minus 1 should look something like that, okay? Actually, let's go ahead and just take a second, and I'll go ahead and put it into the calculator, and we'll actually look at it. Let me go ahead and change the window. I went ahead and plugged it in. See, there we go. Okay, let me see if I can get this to where the glare is not. There we go. Let's go ahead and change the window. I recognize that it's, let's go -1 to 3 is probably good on the X. On the Y, let's go -2 to 2. And then let's go ahead and graph it. Here comes the cubic. All we know is that that's just been a horizontal shift over 1. Here comes the x minus 1, the linear. And we see the fact that there are two distinct regions that we need to find the area of. Here, and of course here. The cubic is actually on top. The cubic is on top from 0 to 1, and the linear is on top from 1 to 2. Okay? Some of you are looking at that and you're thinking to yourself, that looks like I may actually be able to use symmetry. And actually you can, but let's go ahead and set it up the difficult way first. Okay? I recognize the fact that from 0 to 1, it's going to be x minus 1 cubed minus x minus 1 dx. And then from 1 to 2, I recognize the fact that it's going to be x minus 1 minus x minus 1 cubed dx. Now on both of those, we can use that cute little factorization technique if we don't want to deal with the binomial expansion of a cube. You should, however, remember how to do that. Pascal's triangle and the fact that it's negative. For a cubic, Pascal's triangle is 1, 3, 3, 1, and the negative means that every other term is negative. So this one, from 0 to 1, should be x cubed minus 3x squared plus 3x minus 1 minus x minus 1 dx, which means from 0 to 1, that winds up being x cubed minus 3x squared plus 2x dx. Because when I distribute this negative, I'm going to get 3x minus x, and then -1 plus 1, right? That becomes a plus 1 once I distribute the negative. And so the constant term drops out. Now, here's the thing. What happens when you flip a difference? Well, when I flip a difference, the only thing that happens is I get negatives, right? It's the negative of the original, and therefore I don't even have to do the work on this to know that this difference is just going to be the negative of this difference. Now remember, the reason why those don't cancel out is they have different limits of integration. This is from 0 to 1, this is from 1 to 2, okay? Now from 0 to 1, and granted this is going to be much easier because I have a 0 in here as part of my limits of integration, and so I have x to the 4th over 4 minus x cubed plus x squared from 0 to 1. Okay, let's go ahead and figure that one out. That one ends up being 1/4 minus 1 plus 1, okay, which of course is 1/4. Here, sorry, I shouldn't have put an equal sign right there. Let's go ahead and do a plus. You know that it's going to be x to the negative x to the 4th plus x cubed minus x squared from 1 to 2. Okay, I should have put that underneath here. Sorry, just have a little problem just being consistent with my notation. Got back on track. Now, if I plug in 2 to the 4th is 16. So 16 divided by 4 is 4. So that's -4 plus 8 minus 4. Okay, and then of course from here, this winds up, and of course those cancel out and wind up being 0. When you plug in the 1, you end up getting -1/4 plus 1 minus 1, and this winds up being plus 1/4, or the total area is 1/2. So you could have actually used the symmetry because those two regions did have equal area. But you know, if it looks like symmetry, but you're unable to actually convince yourself that you know 100% that it is, you still could have done both of those and wound up with exactly the right answer. Okay. Now, let's go ahead and move on to another one. All right, let's go ahead and do this one. Let's say we're given, f of x is equal to x cubed minus 10x, and you're given g of x is equal to 6x. Okay. Well, I need to know where those cross. Now, if you remember, we should always stop and think for a moment before we continue on. Stop, think, then do, right? Well, look at these. What do you notice about that function? Okay? And I know that you love it when I ask that question. What do you notice about that function? I notice that it's a binomial. I notice that it's cubic. But more than that, I notice that both terms are odd degree. If all of the terms in a polynomial function are the same degree, that says something about, or the same whether odd or even. If they're all odd or they're all even, it says something about its symmetry. This is an odd function. This has origin symmetry, okay? Well, so does this. I mean, it's kind of an underwhelming example of it, but this also has origin symmetry. So that actually should tell me something. I should notice that this is going to be a cubic. It's going to have 3 zeros. Those 3 zeros are 0, positive root 10, and negative root 10, right? Because if I were to factor out an x, I would be left with x times x squared minus 10. And even though it isn't officially the difference of two squares, I can force factor it and give me the zeros, okay? So we already know what this one looks like. It looks like this, right? It's a cubic with a positive, and your negative root 10 is over here, and your 0, and then like negative root 10, 0, and positive root 10. And of course, root 10 is just a little bit bigger than 3. And then you have basically 6x. Well, 6x is pretty steep, okay? And so it's going to kind of run up like this. And you know that the cubic is eventually going to cross it. And you suspect that those points are going to be symmetric. Well, let's actually go ahead and confirm that analytically. And you know that x cubed minus 16x is going to be x plus 4, and x minus 4. Okay, well, this one looks similar enough to the last one where I'm going to go ahead and use the symmetry that I know exists in order to actually just do one of these regions instead of both, and then multiply by 2. Now, obviously, the one that's easiest to do is the 0 to 4, because otherwise I have to deal with a negative limit of integration being negative 4, right? So let's do 0 to 4. Now, obviously, from 0 to 4, I know graphically, since I know what the graphs look like, graphically I know that my linear is going to be more positive. My linear is going to be on top. Of course, I could, on this interval, go ahead and confirm that using, a representative number from the interval 0 to 4. Okay, well, let's use 1. If I plug 1 into here, I get 6. If I plug 1 into f, I get negative 9. Okay, so that's confirmation that g is going to be on top. So I know it's 6x minus x cubed minus 10x, okay, dx. And then, of course, I'm going to have to multiply that bad boy by 2 in order to get the whole, the entire area. So let's go ahead and simplify that integrand. I know that it's going to be negative x cubed plus 16x dx. There's a reason why that looks familiar. So I have 2. I'm going to have negative x to the 4th over 4 plus 8x squared from 0 to 4. If I go ahead and plug in 4, 4 to the 4th is what? Well, I know it's 4 to the 4th over 4, which is 4 to the 3rd, which is easier to think of in your head. It's 64, right? So we have 2, and we know that it's negative 64 plus, well, when 4 gets squared, it's 16. 16 times 8, and if you don't want to figure that out the long way, that's 2 to the 3rd. 16 is 2 to the 4th, so that's 2 to the 7th. So that's 128 minus 0 plus 0. That, of course, doesn't matter. I know that this is positive 64 times 2, so your area is 128. Now, you got to remember that you can actually use your calculator on these, okay? And I'm going to go ahead and remind you how to do that. Now, the functions that we were given was x cubed. Let's go ahead and put that one in y1. You have x cubed minus 10x and 6x. Now, if I go ahead and go back to Zoom 6, I see there's my cubic, and here comes 6x. And of course, if I wanted to see it much better, I could change the scaling. I would just have to, stretch it out and shrink it down, stretch it out horizontally and shrink it down vertically. We have a couple of seconds. Let's go ahead and do that. Let's go negative 5 to 5, and maybe negative 25 to 25. Let's do that by 2s. And that's going to make it look a little bit nicer. And notice again, see the zeros just a little bit outside, negative 3 and 3. Okay, now let's go ahead and go back to the main screen. And we know that our integral is right here in alpha f2. Let's go ahead and do the integral. And let's go ahead and do 2 times the integral. So we go ahead and get the answer that we need. Go 0 to 4. Now, since these are already plugged into my y equals screen, I can just go to alpha f4, the linear, minus the cubic dx. And once I do that, boom, 128. Such a simple one, it didn't really have to chew on it for very long in order to actually spit out the correct answer. Okay, so in order to actually do ones where there's an intersection within the interval, where there are 2 separate regions and f and g behave differently on those particular intervals, we simply have to find those pieces, find those points of intersection. If there's symmetry, we can use that to our advantage. If we don't see the symmetry or there is no symmetry, we simply just go ahead and go along with it as we would otherwise do it. Just split it up into however many separate integrals we need it to be. In the coming videos, we'll go ahead and sort of round out our unit on the area between curves, and we'll move on from there to the section on volumes. So look forward to that.